Welcome, I'm Donna Hamlin, CEO of Boardwise, and I'm here today with my two colleagues and subject matter experts, computational scientist Dr. Tony Drummond and decision scientist Brian Barnier. We're here today to share with you some better ways to ask smarter questions of management about artificial intelligence, AI, and how to discern when to count on it and when not to. With whatever background you might have in AI, you probably know first that AI is almost magically enchanted. Second, that troubling ethical questions have been raised in its use in screening out job applicants. And third, that despite many millions spent, the business benefits are not always as are hoped. We've entitled this Why AI is Stupid because of those mixed results today. And our intent in our conversation is to enable you to guide your management to secure better results from AI. Tony, would you set the stage?
Sure, Donna. We should start by looking at what AI is and its purpose, which was for science and engineering to make intelligent machines or computers. The thought was that to make intelligent computer programs that make a computer think like humans. Brian?
Adding to that, notice the last part of the definition. It's focused on computation and then achieving goals. Now make note of that now to recall later when it becomes important in our conversation. Ever heard an odd music recommendation in your playlist? For millions of people, that's the sound of AI breaking. Because AI really isn't intelligence, it's just math. And that math predicts better for an average person than for you individually.
Yes, so it's important to know where AI is awesome and then how to spot its hazards. It helps to take a look at deeper issues that are hurting AI and other projects. Tony, to help, please share a bit about the origin story of AI.
Okay, so the first approaches to AI came about in the mid-1950s under the concept of encapsulating knowledge. Like an expert chess player, the rules of the game are well known and giving the computer enough knowledge to formulate its own strategies. Then in the 1960s, the rule and goals evolved to create a semi-intelligent conversations, like a computerized therapist. Brian?
Yes, now that therapist was named Eliza. It was pattern matching using the reflective questioning method of psychology. Now, what is interesting is that users felt the software had feelings. And by contrast, the inventor, well, he grew more skeptical. Tony, what happened next?
Let's now jump to the expert systems, which were the first shots at commercial applications in AI. They appear in the 1980s. It involved encapsulating knowledge for field experts and creating recommendations and monitoring systems. These systems can drive computational engine, and thus this can become very computationally expensive. By the end of the 1980s, there were already a number of different commercial applications of artificial intelligence.
You mentioned a number of applications of AI. Could you name a few?
Besides the proliferation of expert systems, also natural language processing, which is a big field of AI today. Speech recognition, computer vision, robotics represented a great technological milestone and a great impact on the manufacturing industry. Planning and scheduling, neural networks, and then we get into deep learning and machine learning. By the mid-1990s, the AI branch of deep learning becomes quite promising. With the help of more computational power, computers were faster and had a lot more processors, and the integration of mathematics and statistic tools. The first applications of machine learning emerged actually in the early 2000s with some very successful stories like search engines and other not so great stories that we'll talk about later. In the field of machine learning, there are three sub-areas if one thinks of the way in which we train or the computers learn from the data partners, namely supervised learning. Computer learns how to classify data. Unsupervised learning. One seeks to find clusters of groups in the data and name them. Lastly, we have reinforced learning, where a computer learns how to best do a task. There are other versions of these three, like semi-supervised learning. Brian, can you walk us through some examples?
This diagram shows 3 examples. For instance, fraud detection is a supervised learning example, and customer segmentation an example of unsupervised learning. Now, language translation is an example of reinforcement learning. Yet, there is another way that people look at this based on the data organization, structured and unstructured. Now, data for structured is what's called tagged or labeled, and this is really pattern matching. Pattern matching means that before the math ever has to determine if a handwritten letter Q is the letter Q, the math already has a database of millions of examples of that handwritten letter Q. Now, having this database and the feedback on accuracy is what's called training.
Yes, and your point also reinforces how terminology can be confusing sometimes. Just as tag and label are different terms for the same action, structure is used in different senses. To some people, structure just means tag or label. To others, structure is the data that has meaning in rows and columns. This contrasts with unstructured data, that is text, such as free-form description of an invoice.
That's a helpful takeaway to write down. When we hear managers talk past each other, we can jump in to bring some clarity. So now we better understand what AI is. Let's identify how AI can be awesome or a hazardous waste of time and money. Let's start with where AI has been awesome, Brian.
So AI is awesome when it has millions of labeled data examples, like the handwriting I just mentioned. So that's translation and handwriting recognition, and they have amazing results. So AI is amazing if and only if the right conditions exist. Tony?
ML works well when we have a very good idea of what we are looking for and are able to assess with confidence what good is. With a good understanding of a system, we can assess causal relationships in the data, and these relationships are preserved over time.
That's a lot of insight. I'm imagining myself in a meeting and trying to remember that. One way would be to draw a smiley face emoji. The circle is the clear and stable boundary of the system. The color is the sufficient and appropriate data. The color can't be scratched across the boundary or leave white space. Then the mouth has a clear cause, a smile, frown, whatever. And overall, the emoji shows results are better when it's easier to verify that what the machine learning thinks is a smiley emoji really is. When we read the word system, we now know that word has a different meaning in different contexts. Brian, what does that mean here?
So here's a formal definition of system. Now let this settle in. Ready? It's a mouthful. A system refers to the causes on the properties and behaviors of an integrated or indivisible whole of its parts. The key here is cause. If something influences or changes an outcome of a system by acting on a part of that system, the cause, then it is part of that system. For example, the sun heats the Earth's crust, air masses, clouds, dropping rain on a road, supporting the tires of a car, influences what? The behavior of driving and the objective of safe arrival.
Going back to being awesome, is it always easy?
Only if those criteria are met. For example, the use of ML to detect diabetic cause disease of the retina has been awesome because the disease pattern is consistent, same always, and it has saved eyesight and medical cost. Yet ML isn't as useful for the disease neurofibromatosis type 2 because the pattern is inconsistent, diagnosis much more difficult for the docs.
Okay, Brian, you took us to limitations. Tony, what other limitations are warning signs to watch?
Mainly what conclusions one can draw from the data patterns that we are observing. In a hot day, lots of people may go to the ice cream parlor, wear lighter clothing, and use sunblock. These 3 actions are direct consequences of a hot day, but they are not correlated between them. Attempting to create a false correlation leads to several problems in ML. In fact, in this case, we can say that one action cannot explain the other action. In a good case, one action may heavily influence another and have a linear relation, or even a nonlinear relation, but that has a pattern, or we can find a pattern. And in some instances, we cannot find any patterns at all. In a nutshell, we don't have a good application of ML when there is not sufficient data to capture all the patterns and correlations, represent dominant features in the data, distinguish random variations from specific causes. So we are not allowed to predict, only to simulate. Brian, you have a good example of this.
Yes, a famous example is why an ML couldn't distinguish between a wolf and a husky. So researchers scratched their heads and wondered what confused the math. Was it the snout? Was it the markings by the eyes? Was it the paws? And this led to the realization that ML is too often a black box. They just didn't know. So then they dug into the math and they found that it was actually the snow in the background of the photos that was confusing the ML. It wasn't even a feature of an animal.
Brian, it seems we have to separate artificial intelligence from helpful artificial intelligence. I'm imagining
Absolutely.
I'm imagining myself in the boardroom trying to remember this. Earlier, we had the hazmat warning sign to jog our memory. How does that work?
So it's 4 items, almost the flip side of the smiley face. First, insufficient data in either appropriateness or amount. Second, correlation that is spurious. It's not the actual cause. Third, that boundaries are wrongly assumed. So the ML is blown up by the surprises when the true dynamics appear, like the rain on the road. And fourth, an unstable system with more variation than the ML was designed to handle. For example, it could handle gentle rain, but not a violent storm.
Beyond asking a few questions with the emoji and hazmat warning sign, what's the next step to understand the benefits and the dangers?
The AI hazard avoidance assessment is designed to evaluate a proposed or existing AI project against a set of criteria to avoid wasting time and money, or worse, making bad decisions as a result of a flawed ML. Plus, there are more potential problems simply because ML is a project like any other project that can suffer problems. Now, Donna, that's your organizational expertise.
Yeah, the big caution is when people and teams are unaware, pressured, or they suffer unusual interpersonal and inter-team conditions, or if they suffer from structural blindness and cognitive bias, including from shifting from academic to business settings. Together, this is implementable. Now let's explore how to more comfortably ask the questions. We'll start with how to get better business outcomes and avoid wasting time and money. Brian?
The key point is to first take time to understand how it works, where it is both a real-life system and the ML that seeks to represent that system. Tony?
How stable is the system and how clear are the boundaries? How well does the data reflect the causes? How well do we understand what we want to learn from the system?
Well, that's crisp. The next reality is that the biggest spend in an ML project is often on data management. Brian, what questions should we be asking about that?
What percent of a budget is for data management in contrast to analytics? How confident are we in the quality of our data? And third, how well do we curate the right data to solve the problem? And last, is there a formal consensus among the business owners of that data as to the ownership of the data and how is the data governed? This cleans up lots of messy problems in data management.
Yeah, I could ask those questions. If management hasn't really thought about this, though, what's the next step to dig deeper?
It's an AI problem data gap analysis. It's 2 ways to think through the challenge of AI projects. Let's look at the diagram. Now, more technical people are likely to start on the right of the diagram with the data, then curate the most useful data, then run the ML analysis, and then try to make a decision to solve a problem. By contrast, business people, like say marketing and sales, are more likely to start on the left side with a problem, then the decisions needed to solve that problem, then the evidence or analysis needed to support the decision, then the data necessary to run the analysis. And this provides 2 ways to evaluate the gap. First, on the right side, we compare the data available to analyze to the data needed to solve a problem. And then second, on the left side, we compare the problem we need to solve to the problem we know enough from data to solve. And looking at both of those gaps helps us get an understanding of are we on the right track or the wrong track. Now, especially in a team setting, this helps people see more broadly, gets people asking questions, seeing the gaps, lots of gaps, being curious, searching for options, and then exploring new pathways.
Well, I can see myself in that process. Together, you've taken us through the core of our conversation. At the same time, you've introduced us to the reality that a mechanical approach to ML can be far different from determining the real problem that needs to be solved in the first place. So let's try a bonus round here and discover what insights flow from decision science beyond ML tools. Decision science really goes to the question about whether a project started with the right formulation. Tony, what experience can you share?
Mathematics can help model the behavior of systems, but it does not have all the whys. We need field experts to further analyze behaviors, the causes. Brian?
The point is that math equations cannot know the human value of a grouping. For example, think about how a young child might sort toys. I'm talking like a 1-year-old, maybe 2-year-old, by shape, size, and color, and how that small child would sort differently each time, depending upon what they value, what's important to them. Now see, AI's ignorance or stupidity, because they don't know this, leads to not only poor quantitative results, but also ethical problems when this reality is overlooked. Tony?
And here are some examples of systems that are heavily influenced by human random behavior. Think of the stock market, fraud detection, user preferences in music or film. While these may have patterns, there are external factors that can dramatically change the predicted course of a system. Brian, how about marketing and sales?
Great one. So here the problem is more than poor results. It's also problems from organizational silos. Too many ML projects done by mathematicians and programmers, but without business research expertise, will wrongly skip over research stages and thus wrongly jump to a conclusion. This, of course, leads to loss from bad business decisions, irritating customers, or whatever. What ML can do by exploring data is to provide areas for researchers for projects that could then inform decisions. Donna, from your organizational behavior expertise, how do you see this?
Well, complications can stack up. Complications in ML projects can add to the complications in the market research projects, and that again can add to the complications to the broader organization. So ML project performance can be improved the way we improve any project, through personality type assessments like our board bona fide does, that's used by corporate board members for determining insights on how to build highly diverse, high-performing teams. And Tony, decision science is a powerful body of knowledge. What do board members most need to know?
3 questions that one needs to ask are, how confident are you of the real problem you're trying to solve? How confident are you that you are asking the right questions? What evidence or data is required to confidently answer those questions?
Brian, if you take Tony's insights to the next step, how do board members help managers make decision science implementable?
Decision science is built on a rock-solid foundation that is in some ways over 2,000 years old. The really hard part for today is getting traction within organizational complexities. Handling, even taking advantage of that complexity, is the design point of the Decision Science Accelerator Workshop, seen here in 4 steps. Now, the first step is vital, identifying the real problem. Almost always, assumptions are made that put projects on a path to waste and loss. Threats include, say, outcome measures that are achievable from a software development sense, but don't solve the real business problem. Now, next is asking the right questions, and that demands knowing how it works, as Tony said. And then, evidence supported by data, as I mentioned in the product data gap analysis. Together, this is a proven and practical path to better outcomes.
You just touched on the product data gap analysis. How does that fit with the AI hazard avoidance assessment?
It's a 3-step process. The AI hazard avoidance assessment, that's the quick and dirty. It starts with the questions we mentioned earlier, and it's usually completed in a focused day, plus prep and follow-up. Second is the product data gap analysis we mentioned. Now, this builds on those findings from the assessment and then surfaces how well a project is benefiting from the proven practical track record of decision science. And then the accelerated workshop itself, now that's 1.5 to 2.5 days. The workshop is the heart of a process designed to achieve 6 months of work in 6 weeks.
Brian and Tony, thank you for sharing your thoughts with the board members today.
Wait, Donna, with your behavioral expertise and seeing across all of Boardwise, Tony and I have a question for you.
Yes, Donna, what do you see as common between thinking through AI functional areas such as risk management, cybersecurity, new product management, and innovation, financial management, and maybe many more?
Well, sure, that's thinking about thinking. For the curious or the reflective person, I ask typically 2 questions. What are the topics or the times that have made you feel mentally imprisoned or at least stuck? Have you ever been perplexed? Have you thought about what being perplexed actually means? To get a breakthrough in value creation, you have to hit that thunderstruck moment when you realize that you really don't know what you thought you did. And what you thought to be true really isn't. Reality is different from your conception. That's the watershed that leads to bigger thinking. To our listeners, thank you for taking the time with us. And as an extra bonus, if you'd like a 1-page crib sheet of the criteria that we've been sharing today that makes an awesome AI project and helps you avoid those that create hazards, reach out to us at our website and we'll be pleased to send you that 1-page diagram. Moreover, it's important to have experts available to help evaluate whether your AI and your management and your board are using it appropriately. And Brian and Tony are always available to work with you on your specific assessments. They guide board risk committees and executive managers on smart use of AI and ways to steer from the hazards. Feel free to contact us anytime for their assistance. Thanks again for joining us. We wish you a smooth success as you discover smart ways to value the benefits of wise decision making.